So yesterday we talked about a permutation. A permutation is when you are selecting certain items in a particular order. So the order of the selection matters. So yesterday one of our examples was about the Olympics and ranking the skiers. So order matters. I mean, if you're at the Olympics, coming in first place is different than coming in fifth place, right? So order makes a big difference there. In all of our problems yesterday, the order that we were selecting something was what we were concerned about. Today we're going to talk about a combination. In a combination, the order that we select things doesn't matter. So in these problems, we're thinking about, like, instead of choosing somebody to be a president, vice president, secretary, where they have specific roles, we're choosing people to just be on a committee. Okay? So it doesn't matter who gets picked first, second, or third, they're all kind of on the team with the same job. Okay? So in a permutation, the order that we pick the things matters. In a combination, it's just that it gets picked that matters. Okay? So in our first example, we're talking about creating some hands of cards. If you are unfamiliar with a standard deck of cards, the next page in your packet has kind of a printout of what the different types of cards are. It's not in color though, so you would need to know or kind of add to that diagram that hearts are red and diamonds are red, and then the rest are black. So we will be doing problems with a standard deck of cards as an example. A lot of times we do in probability because there's so much that we can talk about with cards. So if you're unfamiliar with those, feel free to use that, print out while you're working on your homework, and when it comes to the test, if you're still uncomfortable with it, then I'll have a printout that you can use during the test if you don't know your decks of cards. So in our first example, we're talking about the standard deck of playing cards. If the order in which the cards are dealt is not important, often it's not in a card game. Like, you just get your cards and then you can arrange them to make them whatever order you want them to be. So if the order's not important, then we're talking about combinations. And it says how many different 5-card hands are possible. We're going to use almost the same notation that we did yesterday for this. Our first number is going to be the number that we're choosing from. So there are 52 cards in the deck. Then we're going to use a big capital C for combination. So yesterday we used a P for permutation, and that meant that our order mattered. Here we're going to use a C, saying the order that we pick the things doesn't matter, we're just drawing cards. And then the last number in it is going to be the number of cards that we're actually picking, which is 5. If you are using a graphing calculator or a scientific calculator, this option is in the same place as the other ones were yesterday, the factorial and the permutation button. If you're using an iPhone or iPod, it doesn't have this option. I'm sure there are free apps you can download. We can also use a formula for it, which is given up above. It's very similar to the formula for permutation that we did yesterday. What we would do is take the total number factorial, and then we want to divide by, like we did yesterday, how many are we not choosing. So if there's 52 cards in the deck and I'm picking 5, I'm not choosing 47, but we also want to divide out how many we are choosing. So there's more divided out of this. A combination will always be smaller than a permutation with the same numbers. Because in a permutation, AB is different than BA. In a combination, those are the same thing. Okay? So a combination will always be smaller. So you could do the factorial division, or you could type it in as a combination on the calculator.
Are we going to have to learn that?
No, if you are just going to be using it on your calculator and just typing it right into the combination, then you don't need to know the formulas for what that button is doing. Yeah, second row down. Okay. So to figure out the answer, I type in 52. I go to the same place as yesterday with the probability menu, and I'm going to choose choice 3 for combination. And I'm choosing 5 cards. So this is the number of possible 5-card hands. So there are 2,598,960 different hands that you could get when playing a game of 5-card poker. The second part of this asks how many of these hands have all the cards the same suit. Okay? So our suits are like hearts, diamonds, clubs, spades. So what we need to do is first, there are 4 suits. We need to select one of the suits to work with. It doesn't matter which suit, we just want them to all be the same suit. So first we're going to select one of the 4 suits to work with. And then we're going to multiply that once we have selected a suit. So let's say we're going for hearts. We would need to know how many hearts are there. There are 13 of them, and from those, we are selecting 5 cards. Okay, this particular hand is called a flush, when all of the cards have the same suit on them, and that is considered to be a really good hand. So we can calculate what this is, same way. So we're going to go and do 4C1 and multiply that by 13C5. So 4 suits and I'm choosing one of them. Within that suit there are 13 cards and I'm choosing 5 of them. There are only 5,148 different ways to do that. That still sounds like a lot, but compared to the total number of hands, that's not very many. So when we have over 2.5 million different things that could happen with our cards and only 5,000 of them do this, that makes this a pretty good hand. Questions on that problem? The next example is the same type of thing, but it's dealing with a 7-card hand. So if the order is not important, then we're working with a combination. How many different 7-card hands are possible? We do 52, C7. This time we're choosing 7 from the deck of 52. So the first number is always how many you're choosing from, and the second number is always how many you're choosing. Okay, your first number needs to be bigger than the second number, or at least the same size. If you do like 7C52, you'll get 0. Okay, the first number has to be the bigger number. And the second one, how many of these hands have all 7 cards the same suit? So same type of question as the last one. First, from the 4 suits, we need to choose one to go for. And then once we've selected which suit we're going for, we multiply that by within that suit there are 13 cards. And we're picking 7 of them this time.
Why don't you have 4?
Because there's 4 different suits that we could choose. So we could go for any of the 4 suits, and then once we're within a suit, we want to take 7 of the 13 cards. All right, I'm not actually going to type those in the calculator to get the answers, just the setup here is good enough, and then you could type them in. Okay. A restaurant serves omelets that can be ordered with any of the following ingredients, and then there's a list of vegetarian ingredients and meat ingredients. Suppose you want exactly 2 vegetarian ingredients and 1 meat ingredient in your omelet. How many different types of omelets can you order? When you place your omelet order, it doesn't matter whether you say like sausage and mushroom or mushroom and sausage, because it's all just going to go in there, right? So the order that you do things doesn't matter here. So that makes this a combination. When the order matters, it's a permutation. But when you're mixing something up, like in an omelet or pizza toppings or something like that, it doesn't matter what order you select them. So, suppose I want 2 vegetarian ingredients. Well, how many vegetarian ingredients are there? I've got green pepper, red pepper, onion, mushroom, tomato, and cheese. So I've got 6 different ingredients there. And from those 6 ingredients, I'm going to choose 2 of them. And I'm going to multiply. Whenever we use the word and in a probability or counting problem, it's going to mean to multiply. So, and I want to choose 1 meat ingredient. There are 4 different meat ingredients, and I'm going to choose 1. Okay, so I'll go ahead and type that one in just to make sure we all know how to enter it properly. So I do 6, I'm going to math and grab the C, 2 times 4, go into math, over to probability to get the C, 1. So there are 60 different omelets I could make. So I talked yesterday about how much like going to restaurants stresses me out. You know, you finally think you made your decision, and then you have like so many more decisions to make, because that's a lot of different omelets you could have if you're not a picky eater. Part B says, suppose you can afford at most 3 ingredients in your omelet. Okay, so this is like a la carte pricing. You know, there's a certain price for the omelet, and then you have to pay extra for each additional ingredient that you want. So you look at how much money you have, and this is as many as you can get. You can get 3 ingredients. But that doesn't mean you have to get 3 ingredients, right? It just means you can. So this doesn't differentiate between meat or vegetarian ingredients. It's just ingredients. So what we'd want to do is say there are 10 total ingredients from which I could choose 3. Okay, there were the 6 vegetarian and the 4 meat, so there's 10 total ingredients. I can afford to choose 3, but I don't have to choose 3. Or, when we use the word or in a probability or counting problem, you're going to add. So, or I could choose only 2. Or I could choose only 1. Or I could choose 0, which is really just basically choosing an egg, right? But I could. So when we see the words at most, we need to think about counting down. That's our maximum, but we don't have to do that. Okay. In terms of calculating these things out, whenever you're choosing 0 or choosing all of something, there's only one way to do that. There's only one way to choose nothing, and it's to choose nothing, right? No matter how many options I have, if I'm choosing nothing, there's one way I can do that, and I can choose nothing. If I'm choosing everything, so if it was like 10C10, there's only one way I can do that, and that is to choose everything. So if you just kind of remember that when you choose 0 or choose everything, there's only one way, this saves you having to type something in the calculator. If you're choosing only one of something, there are however many ways of doing that. You don't have to memorize this, but if you do, it just saves you time of typing things into the calculator. Okay? So if you're choosing only one of something, there are that first number of ways of doing that. And then the other 2 I would still have to type in the calculator. But it saves me a little bit of button pressing if you learn to recognize those. So on the calculator for this one, I would do 10 C3, I can afford 3, or 10 C2, or 10 C1 is just 10, and 10 C0 is 1. Add that up, and there's 176 different omelets I could afford. Okay? You're taking a vacation. You can visit as many as 5 different cities and 7 attractions. You want to visit 3 cities and 4 attractions exactly. So how many trips can you take? So how many cities are there? 5, and from those, I'm going to choose to go to 3, and it doesn't matter what order I'm going to the cities. I just want to go there. I don't care where I go first. And, so I'm going to multiply. I want to go to 4 attractions. There are 7 attractions, and I'm going to go to 4. Okay. Think of the word and as multiplication. So when I see this word and in here, that means that I'm going to multiply those things together. Of the 5, I'm going to go to 3, and so times of the 7, I'm going to go to 4. Okay. I'm not actually going to type that in. Going to part B. Part B says, suppose you want to visit at least 8 locations. You don't care if they're cities or attractions, but you want to go to at least 8 places. Otherwise, you feel like your vacation has been boring. Okay, you're a very busy person. You want to do a lot of stuff. So we need to know how many total things are there. There's 7 attractions in 5 cities, so there's 12 different places we could go see. Of those 12, I want to go to at least 8. So I want to go to 8, or add up. Am I going to count up or count down?
Down.
I want to go to at least 8.
Oh.
I'm going to count up because I would want to go to 8, or 9, or 10, or 11, or I want to go to all 12. It's a lot of button pushing on the calculator, so this is where those shortcuts can be helpful. The only way to choose to go to everything is to choose to go to everything, so that last one is going to be 1. Right? When you're choosing all but 1, there are the first number of ways to do that. So that 12C11 is going to be 12. The other ones I would have to type in the calculator. I don't know them off the top of my head. But if I can at least save a little bit of button pushing with those last options, that will help. If you don't remember that, then that's fine. You just type it all in. Okay? I'm not going to take the time to do that right now. So look for the words at least or at most, and think about either counting up or counting down on that. Okay? A theater is staging a series of 12 different plays. You want to attend at least 3 of the plays. How many different combinations of plays can you attend? Now, there are 2 different ways to do this problem. One way is to do it like the last problem. And say, of the 12, I want to choose to go to 3. Or, since this is at least 3, I need to count up. So then 4, 5, so on and so on, until we get all the way to choosing all 12. That's a lot of stuff to type in. Okay? So that's one way to go about the problem, but there's a whole lot of button pushing to do there. So another option for this problem is to think about what we don't want to do. So I would not be happy if with all these plays, I only saw 2, 1, or 0 plays, right? Because I want to go to at least 3. So what we're going to do is think about what would I not be happy with. I would not be happy with 2, 1, or none. And we're going to subtract that from all of the decisions we have to make. So when I get the brochure of all the plays that are there, I have to look at them and I have to think, do I want to do that, yes or no? So each play I have 2 choices. I could either say yes or I could say no. So I look at the list and I'm like, Romeo and Juliet, yes, definitely yes. And then like I just keep on going down. Wicked, yes. And just keep on going down. Les Mis, yes, no. You know, you make your decision each one. Okay? So each one you have a decision, yes, no. So since we have 2 choices to make, we're going to do 2 to a power of how many times do I have to make that decision? I have to make that decision 12 times. Either one of these, the blue one, if you do all the stuff that comes in those ... dots, or this purple one will give us exactly the same answer. Okay? The purple one takes a little bit more thought to set up, but it's a whole lot less button pushing. Okay? So the idea here is I have to make the yes or no decision 12 times. And from that, that's my total number of choices I would make. I want to subtract out from that the stuff that I want to end up not happening. When I get to the bottom of that list, I want to make sure that I have selected at least 3. So I don't want to select only 2, 1, or 0 from that. If you remember your shortcuts, then there's even less button pressing here. There's no shortcut for 2 that you guys know, but choosing 1 gives us the first number, choosing 0 gives us the last number. So then that's not very much stuff to type in at all here. So we'll go do that. So I need to make the yes or no decision 12 times. And from that, I want to subtract, and I'm going to put parentheses here. I want to subtract choosing only 2 from the 12, or choosing 1 from the 12, or choosing none from the 12. So there's 4,017 ways that I could go see plays at that particular showing and be happy. Okay? Last one here, a restaurant offers 6 salad toppings. On the deluxe, you can have up to 4 toppings. So how many different combinations of toppings can you have? So I don't have to have 4, but I can have up to 4. What I cannot do is have 5 or 6. Okay? So 2 different ways to go at this problem. Since it's kind of small numbers, it's not that much of a pain to think about all the stuff you could do. So you could choose to have no toppings. That's really boring. You're just having lettuce. You could choose just 1 topping. You could choose 2 toppings. You could choose 3 toppings. Or you could choose 4 toppings. Okay? That's not tons of stuff to type in, but it's still, maybe more than I want to. So like the last problem, what we would need to do is for each of the toppings, look and decide yes or no. So bacon, definitely yes. Mushrooms, definitely no. Right, like I go down my list at each thing, I'm deciding yes or no. So I have 2 choices to make, and I have to make 6 choices of that. Okay, I have to decide yes or no for each of the 6 toppings. I want to subtract out the things that I don't want to end up happening. I cannot say yes to 5 of them or 6 of them because I'm not allowed to. I'm only allowed to have up to 4. If we remember our shortcuts, when we select everything but 1, that's the first number away. And when we select everything, that's just 1 way. So then this becomes very little button pushing. 2 to the 6 is 64. Minus 7 is 57 different salads I could have. Okay. Yeah?
When do you know when to add them and when to multiply them?
It's funny. The word or is going to be an adding word. The word and is a multiply word. So I could have 0 toppings or 1 topping or 2 toppings, and we're going to add them. When you see the word and, I want to do this and this, then we multiply them. Okay? Good question. This particular topic goes really well with it being March. So nobody's in it anymore. Everybody got busted. But $1 billion was offered for a perfect bracket this year. So when you're setting up your bracket, you have to look at every game and you have to decide this team or this team, this team or this team, this team or this team. So you have 2 decisions to make for each game, right? 2 decisions to make. There are 63 games in the regular tournament, not counting play-in games because those don't count on brackets usually. So in the regular tournament, there are 63 games. The number of possible brackets ends up being 9.2 times 10 to the 18. Or that would be 9, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 zeros. That is 9.2 quintillion different brackets that could be filled out, and this is why they were not very scared in offering $1 billion for a perfect one, because that is, you don't have good chances, right? So that fits really well with this time of year to talk about that.
He said he was willing to offer